Hello friends, I am Amiranwan Nizami and today we are going to start the lecture 2B in which we will derive the governing equations for Euler-Bernoulli beam using the principle of virtual work. So in the previous class, in the lecture 2A, we have done the governing equations we have derived using direct method. Now we will use the principle of virtual work to obtain the governing differential equations. Okay, let's start. So what we have, if you remember, the displacement field of Euler-Bernoulli beam. Bernoulli beam. So first of all, we write the displacement field for that. Displacement field. What is that? U of x comma z, that was equals to minus z times del w naught of x by del x. Okay, and transverse displacement w of x comma z was equals to w naught of x. Yeah, we have found using the applied the assumptions in the first lecture, and we have seen this displacement field. Okay, what is the strain we will have? Strain field, what we will have? We can say strain displacement relations. We can write strain displacement relations. Okay, so the strain we have only here is epsilon xx because gamma xz was 0. Yes, so we have only epsilon xx, and that epsilon xx is what? That is equals to del u by del x. So del of u of x comma z by del x. Yeah, so that would be equals to del by del x of this part. So minus of z times del 2 w naught of x by del x square. So we have the strain as this. Okay, now what we know? We know the stress-strain relationship using the Hooke's law. Stress-strain relationship using Hooke's law. Using for the one-dimensional beam. So what is that? The stress sigma xx equals to Young's modulus of that material E times epsilon xx. As we are studying the homogeneous and isotropic beam, so E would be constant. That is the homogeneous and isotropic. Now, sigma xx equals to E times epsilon xx. What is epsilon xx? Just we have written here, epsilon xx is minus z times del 2 w naught by del x square. So minus z times del 2 w naught of x by del x square. Okay. So finally we have minus of Ez del 2 w naught of x by del x square. Okay. So this is our sigma xx. So we have three things. First, displacement field we have written. Second, strain displacement relations we have written, and then the third is stress strain or stress strain displacement relationship we have done. Okay, using the Hooke's law. Now the fourth stage is applying the principle of virtual work. Applying principle of virtual work. Okay, that is delta work internal minus delta work external is equals to 0. Okay, so we will apply delta work internal. First we will write what is the internal work done. That is equals to integral delta epsilon xx transpose sigma xx. Okay, and there is no other strain and stresses, so only this would be there with the volume integral. Okay, and dv. Okay, so now we can integrate it with three parts: x, y, z. Okay, and dz, dy, dx. Now we know, when we have studied, we have assumed that the width of the beam along the y direction, the beam is very, very thin. Okay, so along that direction, so constant width b, we will integrate it. Y, we will integrate, we will get the b. So we get b outside. Okay, that's a constant value. And now we will do with the x and z function. Okay, x and z. Okay, so now we will have x z remaining. Now delta epsilon xx transpose. What is that? Delta epsilon xx. What is epsilon xx cost? This is the epsilon xx. Yeah. So what we will get if we write delta epsilon xx? Let us write it here. Delta epsilon xx would be equals to what? Minus z times del 2 and the virtual part, that is delta 2 delta w naught of x by del x square. This would be the delta epsilon xx. Yeah. So delta would be gathered with the unknowns variable with of the function of x. Okay. Now coming here, so delta epsilon xx is what? Minus z times del 2 delta w naught of x by del x square. Yes, we get this. Okay, multiplied by sigma xx. What is sigma xx? Just we have written here, sigma xx is minus of ez into del 2 w naught x by del x square. Okay, so minus of e into z del 2 w naught of x by del x square. Okay, and dz dx. Okay, now we have integral b. Okay, we can do one thing. We can take all the z function in one integration, the one integration z integration, and this is minus z, and here it is also minus z. E is a constant value, it will come outside. Okay, and under z integration what we have? Z square dz, and then the other integration is the integration of x only, which is a function of x, which is del 2 delta w naught of x by del x square multiplied by del 2 w naught of x by del x square dx. Okay, this is the remaining part. Okay, now this b into e is a constant outside, and this is the z square dz, and z is integrated from where to where? It is from minus h by 2 to plus h by 2. Okay, so at this position bottom it is minus h by 2, z is minus h by 2, and at the top position z is plus h by 2. Okay, so the thickness coordinate would just be from minus h by 2 to plus h by 2, it will vary. Okay, now we will have delta work internal. We will write it again. What is that? Z integration from minus h by 2 to plus h by 2 b into e z square dz, and then what is the integration only of x? So that is del 2 delta w naught of x. So first part is virtual, okay, del x square, and second part is del 2 w naught of x directly, okay, upon del x square dx. Now this part if we integrate with respect to z, what we will get? We will get z cube by 3. Okay, so let us say it is z cube by 3, and from where to where it is integrated? Minus h by 2 to z equals to plus h by 2. Yes, so if you put the values 1 by 3 outside, and it would be h cube by 8 minus, and minus of that would be plus h cube by 8. What it would be? 1 by 3 outside, 2 h cube by 8. Okay, 2 4 the 8, so it would be h cube by 12 we will get from there. So we will write be into this portion, complete integration would be h cube by 12. Okay, integral x del 2 delta w naught of x by del x square into del 2 w naught of x by del x square, okay, whole dx. What is this? If we write e first, let us say, and then we write b. So b h cube by 12 for a rectangular section, it is moment of inertia, second moment of area. So we can write e into I. Okay, integral x del 2 delta w naught x by del x square. Okay, then del 2 w naught of x by del x square dx. Okay, now at this point when we reached here delta work internal, so let us just focus here one thing. When we will use FEM, we will stop here. Using FEM, we will stop here. Okay. but now we have to get our objective is to get the governing equations of the beam. So we will move forward, and what we have to do here, now we have to focus one thing here. Let us know, because here we stop and think what to do now. We have to take the integration by parts. Okay, and integration by parts in such a way so that one should get higher derivatives and other should be independent of the derivatives. So which should be independent? Where the virtual displacement is occurring, we have to make it independent of the derivative. Remember, we have to make it independent of derivatives. Okay, so it should be free from the derivatives. Okay, so it would be only w naught of x, delta w naught of x, not the derivative. Okay, that is our main objective during the integration. So we will apply UV rule by parts, UV rule of integration by parts. Okay, so we will write again this portion. Let us write delta work internal is what we have written, x times EI is outside, del 2 delta w naught of x by del x. Okay, del x square into del 2 w naught of x by del x square dx. Now let us apply UV rule, U integral V. Okay, so U integral V, we will choose it U and we will choose it V. Okay, so what we will get, U, EI would be there outside, EI del 2 U del 2 w naught of x by del x square U integral V. Integral of V would be del of delta w naught of x by del x. Okay, it would be the integration minus integral del u by del x. So del by del x of u. So del by del x of u is what? Del 2 w naught of x by del x square. Yeah. Integral v. Integral v would be del of delta w naught of x by del x. Yeah. If we integrate it, so it would be this one, and the whole integral dx. Okay. x0 to L. Okay. It is integrated by x0 to L. Okay. Now further, it is the boundary. This is the boundary condition from x equals 0 to x equals to L. Okay. Now let us say this is the boundary conditions VC1. Okay. This is the boundary values. Now we have the under the integration will solve. So we will, this one will remain same. VC1 we will write it. Okay. And now this integration. Now we reached here. Let us see one thing. Should we stop here or should we move ahead? Okay, so we will again focus here. What we have to see this virtual part. So it is yet having the one derivatives, del by del x. What we have to do, what was our target, what I have written here, we have to make it independent of the derivative. It is yet having one derivative, so we will remove one more times. Okay, so yet having one derivatives, so we will remove it. We will remove it. How we will remove? Again, integration by parts, UV rule we will apply. Yeah, so do again. So UV rule, U integral V. So U del by del x of del 2 W naught by del x upon del x square. U will remain same. U integral V. Integral V would be delta of W naught of x. Okay, so this would be the V chosen and this is the U chosen. Okay, now so this would be integrated, and from where to where? It is x equals to 0 to x equals to L. Okay, minus, and minus outside was there also, so that would be plus integral of x del u by del x. So del by del x of this portion. Okay, so del by del x of this one is what? Actually this is the del 3w by del x cube. So we have del 3 and EI is outside everywhere. Okay, sorry. So EI is also there. EI is a constant, we will take it outside. EI del 3w naught by del x cube. Okay, and then what? Integral of V. Integral of V is what? Del of w naught of x whole dx. Okay, so now we can write delta work internal equal boundary condition 1, boundary values 1, sorry, minus boundary value 2, and then what is there? This is a Vc2, let us say, and then it is further plus ei integral x del 4 w naught by del x 4 w naught of x by del x 4, okay, and then delta w naught of x dx. Okay, now what is delta work external? Okay. So if the beam is applied with the external work, then let us say some transverse load q of x. Okay, we are just talking about the transverse load, let us say. Okay, so what we will have? We will have integral delta w naught of x, okay, into q of x dx. Yeah, this would be the external work done. Now, what we have, if we write virtual work principle, delta work internal minus delta work external should be equals to 0. So delta work internal and external. So let us remove the Vc1, Vc2 because that's the already boundary values. So we are ignoring it, and now we are concerning only the integral part values. So ei integral x del 4 w naught of x by del x to the power 4, okay, delta w naught of x dx minus integral x delta w naught of x qx dx. Okay, what we can write it again? We can write in a single integration still, and this delta w naught of x would be common in both. Just go out ei del 4 w naught of x by del x to the power 4 minus q naught of x, and outside would be delta w naught of x dx, that should be equals to 0. Hence we know that this w naught of x cannot be 0. Okay, if this is 0 means no need of analysis. Yeah, so that is what it implies, that this internal part should be equals to 0. Okay, so this is called the Euler-Lagrange equation. It is called the Euler-Lagrange equations. Okay, so ei del 4 w naught of x by del x to the power 4 equals to q naught of x. That is what we got the governing equation of the Euler-Bernoulli beam. Governing equations of Euler-Bernoulli beam. Okay. Hence I have just removed this boundary values, but it has the meaning. Yeah. So if you will see here, so this is what it is showing. It is showing the ei del 2 w by del x square is the moment. Yeah. So bending moment. So moment at which position? It is at x equals to 0 and x equals to L. Okay. So moment, and corresponding to that, what it is showing, del of del w naught by del x, that is the rotation. So moment and rotation. Okay. So moment, and let us say this is the rotation theta. At which position? Let's say at x equals to L. Okay. Then minus moment and rotation at x equals to 0. Okay. So this both position L and theta. Then similarly, if we see the second boundary condition, this is what boundary values. This is telling it is del 3 w by del x cube. That is what shear force. Yeah, that is the shear force, and this corresponding to that is the transverse displacement. Okay, delta w naught. So shear force and w naught at x equals to L minus shear force and displacement at x equals to 0. Okay, so any beam is there. Okay, so corresponding to that, if there is any load, external moment, or the shear force acting corresponding to that at that point. Okay, so this is what it is implying at the boundary values. Okay, it is externally applied. So we are ignoring it because we have only the transverse load acting here, so we are not caring about that right now. Okay, so that is what we got the governing equation of the beam using the principle of virtual work. Okay, we have stopped here, and in the next class, inshallah, we will see with the total potential energy approach.